So I have some data here. In this table, I have seconds. After 75 seconds, our object or particle or something has traveled 5 meters. Here, after 120 seconds, it's gone 8 meters. Here, after 270 seconds, it's gone 20 meters. And I'm interested in plotting this on some type of a graph. And I'm curious about what should be the scale of that graph should be. And they give us some options for different ways to draw that graph, or different axes to draw that graph on, scaled to different degrees. So for example, graph A, we have a scale of 1 for both axes. Graph B, we have a scale of 50 for the seconds axis, and we have a scale of 2 for the meters axis, and so on and so forth. And what I encourage you to do is pause and think about which of these graphs is most appropriate, and which of these scales really is most appropriate for the data that we want to plot right over here. Well, all of the data is positive, so I can think about it in terms of the positive vertical axis and the positive horizontal axis. And so the way we're thinking about it is that the seconds drive the meters. So this is the independent variable. This is the dependent variable. So we could plot the seconds on the horizontal axis. I'm going to try to make sure I have enough space to draw several of them. And then, so that's our seconds axis. And then on the vertical axis, I could plot the distance in terms of meters. And let me just make it some generic lines here. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Actually, I could draw that a little bit neater. 6, 7. Let me copy and paste this. So copy. Let me paste it a couple of times. So this 2 times. And then let me do a third one. And now let me do a fourth one. And let me match up the scales according to what they have here for the different graphs and see which ones make sense. So first of all, we have graph A. So let's say that this right over here is graph A. It's a scale of 1 on the s-axis. So this is 1, 2, 3, 4, 5, 6, 7. And a scale of 1 on the m-axis, on the meters, I should say, on the distance. 1, 2, 3, 4, 5, 6, 7. So let's try to plot this data here. After 75 seconds, we've gone 5 meters. Well, 75 seconds on this scale it's actually not even going to fit on this screen. It's going to be to the right of your monitor right over here. So this data doesn't even show up here, and these are even further to the right. So none of my data would actually even show up on this right over here. Now I could try to do something. I could try to do something like this. I could try to do something like this, where I skip some, and the way that that's normally denoted is you put a gap. You put a gap right over there, and so you do something like this to show that you've skipped a bunch of stuff. And so we could still make our scale 1 second. So this would be, let's say this is 75 seconds, 76 seconds. Notice I skipped all the way from the origin to 76 seconds, 77 seconds, so on and so forth. And then I could plot this first point, 75.5. 75.5 would be right over there. But then the second point I still won't be able to plot. 120 still won't fit. It's going to be way out here. And then actually 8 doesn't fit either. 270 definitely doesn't fit on the time axis. And 20 definitely does not fit on the vertical axis. So I could definitely rule out this scale, actually for both of them. Now let's think about B. Scale on the s-axis is 50. So let's say that this right over here is graph B. So this would be 50 seconds, 100 seconds, 150 seconds, 200 seconds, and then 250 seconds. And then this is 2, 4, 6, 8, 10, 12, 14. So let's see if this is reasonable. So we have, after 75 seconds, we've gone 5 meters. After 75 seconds, which is right around here, we've gone 5 meters. So that's working out. After 120 seconds, we've gone 8 meters. 120 seconds, we've gone 8 meters. So that looks reasonable. And after 270 seconds, we've gone 20 meters. So 270 is 50, 100, 150, 200, 200, 250. This is 300. So 270 is going to be right around here. We've gone 20 meters, which would be right about there. So I could elongate the vertical axis a little bit, and most of my data would fit. So this doesn't seem bad if I were to elongate this a little bit. If I were to go a little bit higher, I'd go 14, 16, 18, 20. So I could plot all of the data. So this seems, I'm feeling kind of good about B. Now let's try to think about C. So C I will do in blue. So let's say this is C here. So it has the same horizontal axis, or same scale, I should say, 50, 100, 150, 200, 250, 300, and then its vertical axis going up by 10. So in the distance axis, 10, 20, 30, so on and so forth. So let's think about these points. So I have this, I have the point after 75 seconds, we've gone 5 meters. 75 seconds, we've gone 5 meters. Then after 120 seconds, I've gone 8 meters. 120 seconds, I've gone 8 meters, so it's right over there. Then after 270 seconds, I've gone 20 meters. 270, I've gone 20. So this isn't bad, although it does kind of scrunch up my distance axis a little bit. It's hard for me to tell the difference between 5 and 8, but at least all my data fit. So I don't know, we'll kind of throw this out as a candidate as well. Now let's think about D. Now let's think about graph D, and I'm running out of colors. Let me see. I could do this in this brown color. I don't know, that doesn't look nice. I'll do it in white actually. So this would be, let's see, scale of S-axis 200, 400. Well, that already gets us above all of our data, so that's fine. And then on the scale of the M-axis, 2, 4, 6, 2, 4, 6, 8, 10, 12, 14. So 75, 75, well, that's about, 75 is about a third of the, little more than a third. 75.5 would put us right over there. Then 128 puts us right over here. So we're really scrunched up along the horizontal axis. And then finally 270, 20 is right over there. So like graph, so this is graph D right over here. Like graph C, we're able to plot most of the data on it, but it feels really, really scrunched up. It doesn't really feel like we're able to notice the differences the way that we would want to, here in the vertical axis and here in the horizontal axis. So A, I could definitely rule out. B, I feel really good about, because I can kind of see the difference in the distances really nicely right over here. C feels a little squinched up along the vertical axis. D feels a little scrunched up, or very scrunched up along the horizontal axis. I'm not kind of making use of my space, so to speak. So I would say that B is probably the most reasonable scale. Let me use the color for B. B is the most reasonable scale for the data that we have here.